Good morning, good afternoon, good evening, everybody. Thank you for joining this webinar, this session called Reducing Technology's Carbon Footprint Through Autoscaling. This is going to be a pretty cool webinar, at least from my perspective, because I love talking about technology. And now I get to talk about something that's kind of not technology, but how it's important for us to think of as technologists. So my name is Frank Yu. I'm the Senior Product Marketing Manager at VMware for the NSX Advanced Load Balancer products. Some of y'all might know this as Avi. We were acquired a few years ago by VMware. And this is going to be nice, but before we start, I have a few housekeeping items that I want to just mention before we get started. Before we start this presentation, I want to point out that there is a Q&A window for you to enter questions during the presentation, and please do enter questions. I love answering questions, and I'll answer them at the end of the session during the Q&A period during this presentation. Also, this webinar is being recorded and will be available online and on demand. We will send out a link to the presentation and the recording afterwards. If you find this content useful, please feel free to share this link with your colleagues. So let us get started. Again, my name is Frank Yu. I'm the Senior Product Marketing Manager for VMware. And we're going to be talking about reducing technology's carbon footprint through autoscaling. As I mentioned in my introduction, this is an important topic for me because I'm a technologist and I love talking about technology and what we can do. But I'm also conscious of the planet and the impact that we have on the planet and everything we do. And I'm sure everybody's seen and talked about companies' carbon footprint, becoming carbon neutral, doing things to reduce energy, to deal with all these pieces. And this is important for us. This is important for us to understand as technologists, because when we look at this, technology depends on power. This is fairly obvious. We need electricity to run everything. I mean, I have a situation, I live and work in a home office, and I have a situation sometimes where when I have all my stuff powered on, my breaker in my house it flips and the power goes out in my office because I'm using so much power, and it's all technology related. It's my computers, my monitors. I have a camera, I have lights, I have a TV in here. I have all these, I have servers, and they consume a lot of power. In fact, you can see the stat here. This is a stat that in general, ballpark plus minus, computers, technology, data centers, network, they consume 10% of the world's electricity. That's a large percentage if you really think about it in terms of everything that we do. 10% of the energy we use is used by computers and technology. That's a lot. What can we do to reduce this? There are a lot of things I think we can do, and we're going to talk about that today. And to give you another example of how much power technology consumes, let's talk about this trend that everybody knows about, crypto mining, Bitcoin. Crypto mining is very resource intensive, running these algorithms, going through these hashes, and trying to get these sequences that basically earn these tokens, which then translate to potentially money depending on how you value it. According to the US government, the White House, they have a report and they said that total global electricity usage for crypto assets, this is all crypto, not just Bitcoin, there's Ether, there's lots of other crypto technologies out there, used between 120 to 240 billion kilowatt hours per year. And that exceeds the energy usage of many countries. It does. So look at this other chart. Bitcoin alone, and this is as of almost a couple of years ago, this number. Bitcoin is using 143 terawatt hours of energy consumption to generate these tokens for Bitcoin. This is more power than a lot of countries use in total. Countries like Norway, 124 versus 123, Switzerland. And when you look at other major apps like Google and Facebook, 12, 5. Just crypto mining by itself is using a huge amount of power. Look at this, the piece above the chart. All the world's data centers, 205 terawatt hours. So Bitcoin is using more than half the power that all the world's data centers use. That's crazy in my mind. That's a lot of power. That's a lot of energy that we're using. And to create that energy, of course, it requires fossil fuels, nuclear power, whatever there are resourceful energy sources like, solar and wind, and but there's a lot of energy being used that could be used for other things. So how can we become more responsible for our energy usage? At VMware, one of the reasons I like working at VMware is because we are very responsible. We're very responsible in terms of the global footprint. For example, we are carbon neutral. In other words, for all the stuff that we use and make and produce, and all the resources that we use, we offset that to make sure that we are carbon neutral. We're not adding more carbon dioxide into the atmosphere. We're 100% powered by renewable energy. And it's not just us internally. We drive this, and the part of this reason we're talking today is we drive this externally. So we have partners that are committing to us and to the world that they are trying to reduce their energy usage and their CO2 output. And the reason is not just because it's cost savings for them, excuse me. And yes, it is cost savings for them, but it's also being a proper partner on this planet. So companies like IBM and Microsoft with their cloud operations and with their other organizations, they are working with us to utilize our technologies to reduce their carbon footprint and their energy consumption through their processes and models. We look at this, excuse me, and first I want to take a look at, well, let's take a step back. As a technologist, as an architect, what do we need? Why are we building all these things? We're building multi-cloud. We're doing modern applications. And when I say modern applications, I mean containers and microservices. We're doing software defined. And we're doing all these things because we're trying to achieve goals. And the goals that we primarily think of when we try to achieve are things like speed. We want to bring things to bear quicker, faster, easier. We want to be able to implement new technologies. We want to take advantage of this quote unquote digital transformation that businesses are going through in translating these brick and mortar processes to technology-based processes. Move from brick and mortar sales to online sales, procurement, management, operations, etc. We're moving so many things to technology, and we need to do this quickly to stay competitive. We also need to be elastic. Elasticity is important for us because we need to be able to breathe. And when I say breathe, scale up, scale down, give that flexibility. When the business has increased demand, these technology resources need to be increased in response. And when demand wanes, we need to pull those resources out in response. We want to do that to be more efficient. Good example is like, for example, when we talk about e-commerce and shopping, we have holiday periods. In the US, we have something called Black Friday, the day after Thanksgiving, which is one of our big holidays in November. And Black Friday is a huge day for shopping. And then the following Monday, Cyber Monday, also a huge day for shopping for the holiday period, where people go out and buy. There are lots of discounts and things going on. And the volume of sales and people going online to buy things increases tremendously. Amazon has their Prime Days. There are lots of other examples, but they need to scale up the resources massively to respond to these events. And it's not just events like that. We also have events, excuse me, we also have events like natural disasters responses. We just had a horrifying earthquake in Turkey. And we need to respond to that in terms of resources, donations, etc. So there's a massive surge going on related to that. And then we need to be flexible. We need to be agile. We need to be able to change on a dime. The competitive market is a situation where it's challenging. And to be competitive, you need to be able to change quickly and easily. You need to be able to change your applications. You need to introduce new applications. You need to do things on a turnaround on a dime to be competitive in today's world. And we need the agility and flexibility in our IT infrastructure to be able to support that. So we need to bring all this together. But then when we do this, we need to think, well, we need to optimize our energy as well. So here I'm showing you an example. In this case, obviously for me, I'm using NSX Advanced Load Balancer, the controller, because we have a separate controller and we have the separate data plane piece called the service engine, which are the little icons in the map, the orange icons in the map. And we have these virtual services. We're hosting the application. And we have these applications, they may sit in multiple data centers or in the cloud as represented in Site 1 around the world. And demand for those applications is going to vary depending upon where it is, where the users are, what the application is, etc., time of day, lots of different variables. And then we have other variables that we need to think of in terms of energy cost. How much does it cost for us to run those applications in those environments and those locations? And it's going to vary. The cost for the application in one location, one region, might be 1.5 times, 2 times more expensive, possibly, than other sites, other locations. And resource demand is going to change. Resource demand might be to higher in one location, one region versus another. So we would like to optimize things to make it more efficient so that those users go to the proper site, but in conjunction with the proper site that makes the most sense in terms of resource access, latency, customer experience, as well as how much does it cost to run that site. So we need to be able to optimize these things. And the load balancer is a great place to do this because the load balancer is really the owner of the traffic distribution for those applications. Let's look at that a little bit. Here I have something showing you, here's all the cool things that load balancers can do. And some of you might use the term application delivery controller, ADC. Load balancer, application delivery controller, in my mind, basically the same thing. Application delivery controller is a term that we use sometimes that is basically a fancy load balancer with fancy features. So let's talk about the load balancer and what we can do for optimization benefits. We have all these functions in terms of traffic management, security, analytics, all this orchestration and automation and other pieces within the environment, within the technology. And we're going to focus on quite a few things here in terms of what we can do for this energy optimization through the load balancer. One is local traffic management, managing the pools of application servers within a certain site. So we can scale up, scale down, provide the resiliency. If something fails for fault tolerance, we can provide that fault tolerance capability. Next, we have global traffic management. This is a good, important piece. Also referred to as GSLB, Global Server Load Balancing. The global traffic management now manages the traffic between multiple sites. So you can do this at a global level, inferred in the name, where you can direct traffic to some sites versus other sites within the global aspect of how this application is being deployed. For the context of this presentation, we're going to skip over the security, even though security is an important piece and it's a huge piece. But I'm going to skip over that in the context of energy optimization. I want to talk about container ingress services. So a lot of things are being modernized. I used the term modern applications earlier. Microservices, container infrastructure, a lot of things are moving. Containers moving pretty rapidly right now. And that load balancer can act as that ingress controller to manage these microservices for application deployment. And that's a key capability. So it's similar to local traffic management, now done at the container level to manage this. And that becomes very important. Next, we have analytics and observer. You can't make changes on the fly, especially if you're trying to automate or script this, without understanding what is going on. You need the insights. You need to understand what is the load on the application, what is the load on the server, what is the CPU utilization, what is the traffic utilization, etc. You need this information to make decisions. And what are you going to do with those decisions? You're going to look at orchestration. So you're going to orchestrate the load balancer with other pieces of your infrastructure. It'd be VMware infrastructure. We'll talk about that a little bit later. And it could be third-party infrastructure as well, because application deployment is a multi-technology and usually a multi-vendor environment. So all those pieces need to work together through the APIs, through logs, whatever pieces, through scripting capabilities to really orchestrate that together. We need that elasticity that I mentioned. We need to be able to adapt to these changes in real time or near real time so that we can adjust appropriately based on time of day, in terms of cost, efficiencies, resource management, etc. We need that resilience. We need that high availability. We need the self-healing capabilities, fault tolerance. This is on a site basis as well as on a local basis. So for example, a lot of people put their applications in the cloud, in the public cloud, because they think, oh, public cloud is great. I'm going to put it in there, and now it's this ubiquitous thing sitting in this ubiquitous cloud, and it's always going to be available. But I'm sorry to tell you, public clouds and clouds have failures. Data centers have failures. There's hardware failures. There's software failures. There's human error, which is a large percentage of these failures. So you need to be able to heal or adjust to these failures in real time if possible. You need technologies like load balancing technologies to help you. And automation, this is a key piece. We need to bring it all together so that you don't have to have someone 24/7 looking at monitors and dashboards and stats and having run books to know that when X happens, do Y. Automate that process. Automate it so that the tool sees what's happening and can automatically adjust the infrastructure by spinning up resources, spinning down resources, moving resource access as appropriate. And all of this ties into the energy optimization, because now we can turn on and off resources, move resources based on the energy consumption, the energy cost, and other aspects to optimize how we're utilizing those application resources and how much energy they are consuming. So let's look at a few pieces of this technology and how it works. Local load balancing, single load balancing fabric across multiple clouds. So multi-cloud is a thing. Many organizations are using multiple cloud infrastructures. Public cloud, private cloud, also known as software-defined data center or SDDC, and combining that to create an application environment, access environment. And you don't want to, if you don't have to, use different technologies and dashboards and programming languages and other pieces to manage each individual component. So what you want, and this is where the load balancer can come in extremely handy, is you want the load balancing technology to make that consistent in terms of how you configure and manage those environments for the applications. without having to understand or know all the details of it because the load balancer is managing it for you. It is acting as that level of separation between you and that infrastructure level of understanding. So you can now centrally manage multi-cloud deployments across a single controller aspect for your load balancer. You can automate those moves and changes. On-prem, cloud, bare metal, it doesn't matter from a load balancing perspective as long as the application is somewhat consistent. You can deploy it and it will figure it out. You can tell it how it works. And you can scale these application instances based on resource demand. So if you have 2, 3, 10 instances of an application in an environment and demand increases, the load balancer will know and it will be able to adjust to tell the system, increase the number of instances of the application so that you have availability for your users to make that customer experience appropriate. This becomes very important as we discuss the scalability and the flexibility for this energy consumption, because it's not just bringing resources up, it's also tearing resources down when they're not needed. If you don't need the resource, why spend the energy and the resource time and the cost, if it's public cloud, to have those resources available if they're unused? Global Server Load Balancing, GSLB, is another critical component because now we're talking about these multi-site things. So again, I talked about multi-cloud. Multi-cloud, we have different public clouds. We have regional clouds. We have regional data centers. And we may have the application residing in all of these locations. So we need to take these pieces and we really need to bring them all together into this one coherent mix. So you don't have to think about, okay, I have 5 instances of the application that can support X number of users in this location and Y number of instances in that location that can support this number of users. And oh, by the way, these users are in this region, North America, and I would prefer them to go to this data center versus that data center, which is across the planet. And I have those users over there. You don't have to worry about that. GSLB, Global Server Load Balancing, can manage that and direct that because it understands and knows where the users are coming from, where they need, what application they need to go to, and it can do the direction for you. It can provide high availability. So typically we think of in terms of multiple data centers, one of the things we typically think of is disaster recovery. I want active, I want standby. If my primary active data center fails, I want to bring up my standby. The standby is not used until it's needed in that emergency situation. But you know what? The standby data center is fully functional. And it could be in the cloud. It doesn't have to be a data center. It's fully functional. So in theory, we could make that active also. Let's take advantage of these resources and make traffic go to both data centers. And if one fails, GSLB knows, directs all the traffic to the other data center that's still working, and increases the number of resources available to make it available for you. So it provides that disaster recovery or active-active capability. I mentioned that, kind of mentioned the geo-based load balancing. So we can direct traffic based on where the user is to the optimal location in terms of where the application sits for them to access it. There's an energy savings there because it's not just access to the application and the application usage, it's also network utilization. Network utilization across all the different hops to get there, as well as network utilization through your infrastructure if necessary. Cloud bursting, so I mentioned this, where we can scale the resources on demand as needed to scale up and scale out. Cloud bursting is not just scale up, it's also scale down to make the resources optimally available in terms of how much resources needed for that application for the load that is being asked of it. And this applies to not just your traditional applications, but again, to the Kubernetes type Microservices container environment. Kubernetes is the orchestration environment that most people use for their microservices container environment, and Kubernetes is very important to integrate within your container environments if you're not already. We need analytics. Again, analytics is key for this to work. So all this information all this traffic that is being sent through these data centers, through this infrastructure, has to give us information in terms of end-to-end timing. What is the round trip time? What is the resource load for these applications in terms of CPU load, network load in terms of traffic throughput, memory utilization? So we know when things are being taxed and not taxed, and we can bring things in and out of service. We can now set thresholds. If round trip time or CPU utilization hits a certain threshold, high watermark, let's call it 80%, I need to add more resources to bring that down. If they hit a low point, let's call it 20%, then I can take resources away, shut them down, because they aren't really necessary to provide the proper performance for the application. Analytics and insights for the application, end-to-end insights for the application, are key for us to understand and be able to do this automation and provide this resiliency and provide this energy efficiency. And this all ties together to this last important piece. Automation self-service. We cannot have these processes be manual. We need the ability to take these systems and these processes and these things and these thresholds and the analytics and provide some sort of quote unquote brain that has the information that you're providing in terms of thresholds and other aspects to be able to automatically adjust. So integrating with VMware's ARIA. ARIA you might have known as VRO, VRA, VMware's vRealize orchestration and automation scripting tools. Integrating with Ansible from a container perspective, or Kubernetes, or any other piece. You can see some examples there on this slide. But we need to take this and make this a closed loop system. Get the human out of the process and automate these things so that it happens based on when and how, where it makes sense automatically. So now this energy efficiency becomes even better because we're providing just-in-time resource allocation for what you need. Let's look at this in a little detail. So if I wasn't using NS Advanced Load Balancer or a full-fledged closed loop orchestration system, I'm going to have a process for bringing up a load balancer and more application capability. I need to know, number one, does the load balancer exist? What's the correct environment? What is the performance I need? What is the capacity that I need? What dependencies on other technologies in terms of security, routing, IP allocation, lots of other pieces do I need to make this work right? And the traditional process, it can take weeks for organization to figure this out and build the process to make this change. And then we have more things. You have to size appropriately. If I need hardware and servers, how big do they need to be? If I'm using the cloud, for example, public cloud, which instance of these servers that I'm putting in the cloud do I need? I need to identify hardware, but there's hardware associated. I need to set up configurations. I need to configure the routing, the firewall policies, authentication. I need to do logging alerts and the analytics. I need to reserve my IPs, and I have to do this for my standby system as well. There's a lot of pieces that we need to do to make something happen, to deploy an application. Now, if you're involved in this technology in this world, you know what I'm talking about. It can be extremely painful. When we talk about what we can do with our automation capabilities and how we can bring this together so much easier, this first step is declare the virtual service attribute. So I need to create a virtual service. It's going to be hosting this application, and I want in these environments, and I want these are the load requirements, etc. Once I got that figured out and I configure it into the system, then the system will automatically do all these other pieces. It will check the existing capacity. It will spin up new service engines, the local load balancers. It will talk to the other components to make sure it's proper in terms of VMware's vCenter, or if you're talking about public cloud, AWS, or Kubernetes for microservices, etc. It will allocate the virtual IP addresses. It will configure the network interfaces, provision the policies. It will integrate with the other security components to make sure they're put in. It'll monitor the performance. That's an important piece, because monitoring the performance means that we have this closed loop infrastructure now in terms of automation, and based on the performance that's monitoring, it will go back and readjust as necessary. And now we're done. It is so much easier to do it this way. Let me give you an example. So I'm going to use a use case. I'm going to use Telco Cloud because telcos own the biggest data centers. So I want to use them as an example. And for VMware's Telco Cloud, we have a solution, Telco Cloud Platform, Telco Cloud Services. And you can see here all the components within it, within the VMware family. Where you have, going from the bottom up, you have vSphere, you have NSX, you have vSAN, which is the storage, you have vRealize Operations, the ARIA, as it's now called, for the operations and the automation. And above that, you have the Cloud Director, you have Tanzu, which is for the Kubernetes piece. You have Telco Cloud Automation, all these components that are tied into this platform. And you have all the applications that are certified for this. You can see at the very top, 275 plus certified network functions for the telcos. Network function, just to if you're not telco specific or understand telco lingo, that's basically an application or a service function like a load balancer or firewall, security, etc. It's an application. And we need to insert the load balancing somewhere within this infrastructure. We need to insert it somewhere towards the bottom layer because it's going to be helping manage all the way through the top. And when we do that, inserting that load balancer. So we can see here now, we have the NSX Advanced Load Balancer control plane. And tying into all these components at the bottom, NSX, vSphere, vRealize, etc. And you see on the right-hand side, NSX Advanced Load Balancer data plane. Those are those service engines, which are actually doing the real work of load balancing these services. Here, I'm load balancing CNFs, container network functions. In other words, it's containerized microservices. But it could be virtual machines in your traditional application environment. And it is now load balancing the traffic. It's getting statistics, and you can see the little dotted line in between. We have a little graph there. It's collecting the analytics. And the control plane component on the left-hand side is now receiving those analytics and creating that feedback loop. So it can tell things, I'm seeing these analytics and I'm seeing these thresholds or these things, criteria being met. I'm going to go around and make configuration changes to the environment because they are necessary to optimize the performance. We have the automation, we have the central orchestration. We're providing the resilience because we have that high availability. We're using local load balancing, and we can include the global load balancing in this infrastructure. And that gives us all these things that we're talking about on the left-hand side in terms of those icons there. Automation, central organization, resilience, analytics observability, and elasticity. And it's all done in this central, unified, simple fashion. So let me show you a quick demo of how this is working in action. And this short demo is not completely full, but it gives you a good idea of the ease and the capabilities within the system. So here I have my demo, and I'll go ahead and start it. You can see here, I'm going to select the network function catalog. I'm using Nginx as that's the application server, my web server. And I'm going to give this network function instance a name. I'm going to call it Nginx workload. I'm going to select a cloud to put it in. In this case, I have this one that's already set up for me. And I'm going to click on next. And now I'm going to go to give this a namespace. I'm just going to give it a default namespace. And I'm going to select a repository for the Kubernetes and everything for the configuration that I have already predefined. And now I have configured this network instance. I'm going to tell it to deploy it. You can see there it goes from non-instantiated to instantiated. Now I can look at that workload and I can look at my virtual services associated that I have associated. And I'm going to select the ones that are associated with my TKG, which is my demo. And I'm going to pick one of my workloads. In this case, I'm going to pick my default workload. You can see here that I have my workloads on the top. And you can see here on the very right-hand side that I have applications that are associated with it. So I have a score in terms of health and capabilities that we define. And I also have 3 instances of the service engines managing that workload. So here I have my virtual service dashboard. I can look at my service engine. Now I can pick one of my service engines. I'm going to pick the one in the middle, which is the MITcb, which is the default. And I'm going to look at it. And I'm going to go to the workload and start looking at the analytics. And now I can see throughput. I can see CPU utilization. I can see the memory utilization of my service engine, the number of packets being received in terms of total number of packets per second, and transmit. And in combination, I can look at the total throughput. How big are these packets? How many bits per second am I going through? So with that information, I can now look at, I have 6 instances of the application running. And based on my workload, I might say, my system might say, I need 10 to appropriately run this. I need more instances of my application to run this. And therefore, my service engines, I might need to add more service engines to make this properly available. So I can scale up in real time or near real time, just in time, using the automation tools. And I can scale down based on the metrics as well. So now I can scale up and down my resources, optimizing how much energy is being utilized for these resources to optimize how much is being done appropriately. And this is really important because in the traditional world, especially in the telco world, let me give you an example in the telco world. In the telco world, the standard model is when something hits 40% utilization, you add more systems for availability and redundancy. And when it goes down a certain percentage, say 5 or 10%, then you can take things out. That's a manual process. The other thing in the telco world is that, and this is true in the enterprise and the other technology worlds as well, is that we tend to build things for overcapacity because we don't want to hit those high threshold capacities. So we're going to build things for these certain capacity thresholds, like that 40%. But if you build in a just-in-time model, now we can build for better thresholds, 80% capacity, 70%, whatever the number may be. But now I don't have a lot of unused capacity sitting there doing nothing and using energy and doing other things that are unnecessary just because we need to or we think we need to. We want to improve that capacity, capability, to provide it so that it's more closer to what is actually being utilized. And that's where the energy efficiency comes in. Cool. So key takeaways for me in this discussion is, number one, technology has massive power requirements. It requires a lot of power. 10% of our total consumption of our energy is used by technology. A lot of that is wasted because it's sitting there idle doing nothing. A lot of it is inefficient because we're utilizing energy in the wrong power grid. We're utilizing energy at the peak times in some locations and then when it could be used in off-peak times in other locations. We can optimize this through insights based on the cost of the power, feedback from the energy grid, for the people and the organizations who own the energy grid to say, we prefer to use power at this times a day because it is going to be off peak or so on and so forth. We can provide cost efficiencies because of this. We can orchestrate and automate all these processes so that we can provide that near real time, just in time provisioning of resources up and down so that we do not have to have an army of people managing this and micromanaging this on a day-to-day, hour-to-hour, minute-to-minute basis. Orchestration and automation is key for us to be able to do this efficiently in these environments that we typically talk about, these large environments. And ultimately, my last point, of course, is that load balancers are key to enabling all this because as you saw, load balancing technologies are critical to bring this all together. We need load balancing technologies to provide access to these application pools and provide application pools and for this global server load balancing. And we provide the agility, the resiliency, the elasticity through load balancing technology. And by tying this within the analytics and orchestration and tying this to understanding the energy utilization and resources needed, we can really improve the energy efficiencies of our applications and IT infrastructure to optimize things and reduce the power consumption. So ultimately, using these technologies, bringing it together, we can make a significant impact on energy consumption and corollary cost effectiveness for our businesses to optimize the energy consumption through the utilization of RT technology. So, okay, let's now take a look at the Q&A and see what questions that we have. And let me see here. Let me pull up the questions. And the first question we have is, what if I'm using non-VMware pieces, third-party components? Can I still benefit? What if I'm not using vCenter and I'm not using the ARIA vRealize components? Can I still leverage this concept for energy efficiency and just-in-time resource demand capabilities? And the answer is absolutely. There are benefits, I believe, to using a system within a single technology family. So if you're using VMware products, they're going to play nicer together. And they're going to integrate better because obviously we work together on the back end within the different technology products to make things more efficient. But ultimately, the goal is that this is a multi-technology, multi-vendor world for IT. And we do need to work with these other components. So if you're using other vendors like Red Hat, or you're using other cloud environments such as IBM Cloud or Google Cloud or AWS, or using other types of technologies and security technologies, whatever the case may be, can you integrate? Absolutely. A lot of them are pre-approved, pre-certified. And as long as you have the proper APIs and hooks to bring these things together, you get them to work right. So the general answer to this is yes, 100%. Even if you're not using VMware components, I strongly recommend that you look at what you can do with what you have. And if one or two pieces, such as the critical load balancing component, can help you dramatically to improve your capabilities in terms of just-in-time resourcing and energy efficiency, I strongly recommend you take a look at it. I'm a little biased, but I do recommend you take a look at it. All right, my second question here, and this is a good question, and I don't know if I have a great answer for this. How much energy can be saved by using this technology? How much energy, money can I save by just, quote unquote, turning this technology on, turning on this capability and letting it go? I don't have a clear-cut answer for you. It depends on your environment. It depends on what you do. It depends on what your applications use and how much they scale in terms of fluctuating up and down in terms of resource demand on a daily, weekly, monthly, yearly basis. It depends upon the regional influences of where this application used, or is your company using this application primarily in one region? Is it global? But if I were to use just a very, very rough rule of thumb, 10, 20% efficiency in terms of energy and resource allocation. Could be more, could be less, but that's probably not a bad starting point for us to think about in terms of how much can I save. And when you think about it, that can be a significant number in terms of the business's budget, in terms of operational capabilities and other pieces. So not a clear answer, but a good ballpark guess from me. And don't hold me to that number if you find your numbers to be different. 10 to 20%-ish resource savings, which would be very good. I have time for one more question. And this question is, will this work in my data center and in a multi-cloud environment? Will this work in an environment that has these different components and different sites and locations and different technologies? So when I talk about this, I already talked about a little bit. When we talk about this multi-cloud environment, we have multiple pieces there that use different technologies. So we have private cloud. Let's start there. We have software-defined data center or virtualization. Of course, we have the VMware family of products that can help you with that. And there are other products from other vendors, and there's open source as well. So we have that environment. We have the cloud. We have public cloud, and we have different flavors of public cloud, and different flavors of public cloud work differently. We have AWS, we have Azure, we have Google Cloud. Those are the three big clouds that everybody talks about, and there's many, many others. And they all work differently. They use different technologies, different configurations, different aspects. But the key I want to tell you is that, number one, yes, you can use all these different environments together, number one. And two, using the right tools, you can consolidate the management and configuration of those different environments to a single platform. And here I'm going to toot our horn a little bit using NSX Advanced Load Balancer. For the load balancing component, we can de-stratify all those components to make it look like a single dashboard, single application, even though that application is going to reside in multiple environments. You don't need to worry about that. This technology understands that this is how AWS works. This is how Google Cloud works. This is how it works in your private data center environment. And you don't worry about that. We will take care of, I know I need to deploy application X in location Y and Z, and that Y and Z are different, and this is what I need to do differently to make it happen. So 100% multi-cloud environments, multi-technology environments, this concept will work, and using the right tools, you can make it easier on yourself by making those environments consistent from your management perspective by separating that control plane and the data plane and bringing it all together. So that's all the questions that I see for today. I appreciate everybody joining the presentation. Hopefully this was useful for you, and hopefully I look forward to seeing you and having you join future presentations that we have on other topics that might be relevant to you, what you're dealing with. So thank you very much. Thank you for your time. We look forward to seeing you in the future. Thank you very much.